Welcome to Study Loop.
Hello everyone, this is a solution to problem 40 of chapter 24 of college physics. Now we're going to pass unpolarized light through two polarizing lenses. And the question is asking, relative to the original incident final intensity, how much do we have to rotate the second polarizer by in degrees in order to get various outcomes at the end over here? So this is what we're working towards. And we're told that light, as it comes in, is unpolarized, which means that it's got electric and magnetic field components oscillating in all directions. So that's what you can see represented over here, as if you were looking at the wave head on. Then it passes through a polarizer, which is polarizing this unpolarized light in some given direction, right? So here I've chosen this direction to be vertical. And so you can imagine this as being some kind of a filter that only allows light in this direction to come through. And so this is the polarization of the wave as it comes through the first polarizer. It's now only oscillating in a single direction. Also, we know that because it went in to the first polarizer unpolarized, the intensity of the light coming through the first polarizer is going to be half of the intensity incident on the first polarizer. So that's why I said that the intensity of light in this middle region between the two polarizers is I0 over 2. Okay, and then what happens is that this wave with intensity I0 over 2 passes through another polarizer. Okay, so what we have first is that actually the direction of polarization of the first and the second polarizer are identical. So we have that all of the waves or all of the components of the wave that make it through the first polarizer also make it through the second polarizer. So what this means is that if theta is equal to 0, then I final, i.e. the intensity of the light coming through the second polarizer, is going to be also I0 over 2. So what we're asked to find is how can we reduce, or what is the angle theta that we need to find in order to reduce IF to various fractions of this value. So for simplicity, let me say that the incident initial intensity that is going through the second polarizer is I0 over 2. Okay, so this is just the intensity of the polarized component of the initial unpolarized wave that is making it through to the second polarizer. All right, and then in part A, what we're asked to find is how can we make the intensity coming out of the second polarizer be 1/2. So 1/2 of the intensity incident on the second polarizer. And now that's I sub I. So this is the incident intensity on the second polarizer. So we know that whenever there is an angle between the polarization of the wave and of the polarizer, then the intensity that comes out on the other end is going to be reduced according to this cosine squared law of the angle between the polarization axis and the axis of the polarizer. So what we have here is that we're just going to call this theta, and we're asked to find what this theta is. Okay, so now that we know that IF is a half of I sub I, we know that this has to equal I sub I times cosine squared of theta. Okay, so then if this is a half I sub I, then I sub I cancels. We can take the square root of both sides, and then we have that cosine theta is equal to 1 over square root of 2. Plugging this into the calculator and taking the r cos of both sides, or the inverse cos of both sides, you see that theta has to be equal to 45 degrees. So that's the solution to part A. Now for part B, you just have to follow the same instructions basically. So you want the final intensity, so the intensity coming out of the second polarizer, to be 1/10, so 1/10 of the polarizer going in. But again, you know that this 1/10 of the initial intensity that makes it through is going to be I sub I times cosine squared of theta. So again, I sub I cancels, and you can take the square root of both sides such that you get that cosine of theta is equal to 1/(10). And when you work out what this angle is, you find that theta is equal to 71.57, or approximately 71.6 degrees. And so that is the answer.